Welcome, everyone. In this brief demonstration, I'll introduce you to serverless computing and show you how to deploy a machine learning model for brain MRI segmentation using Google Cloud's serverless products. Let's start by understanding what serverless computing is. It's a cloud computing model that allows developers to build and run applications without managing server infrastructure. The cloud provider automatically handles scaling, patching, and server management. This means you can focus solely on writing your code without worrying about the underlying infrastructure. Google Cloud offers two main options for serverless computing: Google Cloud Functions and Cloud Run. Let's look at each of these. Google Cloud Functions is an event-driven compute service. It's ideal for running small pieces of code that execute in response to events such as HTTP requests. Cloud functions are perfect for short-lived and stateless tasks. On the other hand, Google Cloud Run allows you to deploy containerized applications. It offers more flexibility by supporting custom server configurations and long-running processes. With Cloud Run, you can package your application along with its dependencies into a container, providing a consistent environment for both development and production. In this demo, we'll use both of these services. First, we'll use Cloud Functions to deploy our machine learning model. The function will be triggered by an HTTP request, which will quickly load the model and return the segmentation results from a brain MRI. We'll set up a Flask web server that interfaces with the Cloud Functions API and displays the prediction in a user-friendly way. Then we'll use Cloud Run to deploy a web interface. This will allow users to upload a brain MRI image and see the segmented image, the predicted mask, side by side on the same web page. Before we dive into the deployment process, let me briefly mention the machine learning model we're using. It's a brain MRI segmentation model trained on a popular segmentation dataset from Kaggle. This model can identify and segment brain tumors in MRI images. While I won't go into the details of the model or its training process, it's important to know that this type of technology can greatly assist doctors and surgeons in identifying brain tumors without manual intervention. Now let's start with deploying our model using Google Cloud Functions. The first step is to upload our machine learning model to Google Cloud Storage. This allows us to access it easily within the Google Cloud Platform, or GCP. Let's now look at the code for our cloud function. The main file is called main.py, and it contains several important components. First, we import the necessary libraries and load our custom model. Then, we define the entry point for our function using the Functions Framework HTTP decorator. Inside our function, we have some important checks and processes. For example, we verify if the uploaded file is a TIFF image, which is a common format for brain MRIs. We also create a temporary file to save the uploaded TIFF image. This is necessary because we need to work with the file on the server. After that, we perform some pre-processing on the image before passing it to our model for prediction. Once we have the prediction, we convert the result to a PNG image. Why PNG? Because we want to display it easily on a web page, and TIFF files aren't widely supported by web browsers. This is different from what you might see in some documentation where they return a string. We're returning an actual image file. Now let's deploy this code to Google Cloud Functions. We go to the Cloud Functions section in the Google Cloud Console and create a new function. We'll name it something descriptive like Brain MRI Model. An important setting here is to allow unauthenticated invocations. This means our function will be publicly accessible, which is what we want for this demo. For the runtime settings, we need to be mindful of our model's size. Since our brain MRI model is quite large, around 400 megabytes, we'll allocate 4 gigabytes of memory and a single CPU to this instance. This ensures our function has enough resources to load and run the model efficiently. Next, we set up auto-scaling. This is where we decide if we want an instance of our function to be always running, or if we're okay with it starting up on demand. If we set the minimum number of instances to 1, it means there will always be an instance ready to respond immediately. If we set it to 0, it means an instance will start up when a request comes in, which can save costs but might result in a slight delay for the first request. The maximum number of instances can scale up to 50, allowing our function to handle many simultaneous requests if needed. For the runtime environment, we'll choose Python. Now for the source code, we'll use the zip file we uploaded to Google Cloud Storage earlier. This zip file contains 3 crucial elements: our brain MRI segmentation model, the main.py file with our function code, and a requirements.txt file listing all the Python libraries our code needs. We select this zip file as our source, and Google Cloud Functions will use it to set up our function. The deployment process can take up to 10 minutes, but once it's done, we'll have a URL that we can use to invoke our model. This URL is the endpoint where we can send HTTP requests with brain MRI images to get segmentation results. Now that we have our machine learning model deployed as a cloud function, the next step is to create a user-friendly web interface. This is where Google Cloud Run comes in handy. Cloud Run is excellent for managing containerized applications, especially web servers. For our web interface, we'll use Flask, a lightweight web framework for Python. This web application will do several important things: display a simple web page where users can upload brain MRI images, send the uploaded image to our cloud function, receive the segmentation results, and display the original image and the predicted mask side by side. Let's take a closer look at the code for our Flask application. The main file is typically called app.py. In this file, we define our API endpoint, which is the URL of the cloud function we just created. We also specify upload folders where we'll store the original uploaded images and the prediction results. Our Flask application has 2 main routes. The home route renders our index.html file, which is the main web page users will see. It's a simple HTML page with a form for uploading images. This predict route is called when a user uploads an image. It handles the file upload, sends the image to our cloud function, receives the prediction, and passes the results back to the web page for display. This code handles file uploads, sends the file to our cloud function, and saves the prediction result. It then returns the file names of both the original and predicted images, which our web page will use to display the results. To deploy this Flask application on Cloud Run, we need to containerize it. This is where Docker comes in. We create a Docker file that specifies how to build our application into a container. This Docker file uses a slim Python image as a base, installs our requirements, copies our application code, and sets up Gunicorn, a Python WSGI HTTP server, to run our Flask app. Now that we have our Docker file ready, let's deploy our application to Cloud Run. We'll go to the Cloud Run section in the Google Cloud Console and create a new service. When setting up a service in Cloud Run, we have 2 main options for sourcing our containerized application. First, we can use a pre-built Docker image from Google Cloud's Artifact Registry or Docker Hub. Alternatively, we can use our source code from a GitHub repository along with our Docker file. For this demo, we'll use the second option. This approach allows us to leverage Google Cloud Build, a service that automatically builds our container image every time we push changes to our GitHub repository. This ensures our Cloud Run service stays up to date with our latest code changes. To set this up, we first connect our GitHub account to Google Cloud. Then we select the repository containing our Flask application. After selecting the repository, we need to specify our build configuration. Since we have a Docker file in our repository, we'll select that as our build configuration. Next, we'll configure our Cloud Run service. We give our service a name like Brain MRI Web App. Then we allow unauthenticated invocations just like we did with our Cloud function. This makes our web application publicly accessible. Next, we set up auto-scaling. Similar to Cloud functions, we can specify a minimum number of instances. Setting this to 1 ensures our application is always ready to serve requests quickly, but it will cost more than setting it to 0 and letting instances spin up on demand. Lastly, we allocate memory and CPU resources. For a web application like this, we might start with 1 GB of memory and 1 CPU, but we can adjust these based on our needs. After configuring these settings, we click Create to start the deployment process. This process typically takes a few minutes because Google Cloud Build needs to create our container image, scan it for vulnerabilities, and then deploy it to Cloud Run. Once the deployment is complete, we can view detailed logs of the process in the Google Cloud Console. These logs are helpful for troubleshooting if anything goes wrong during deployment. After successful deployment, Cloud Run provides us with a URL for our web application. This URL is publicly accessible, allowing anyone to use our Brain MRI segmentation tool. Let's test our application. Open the provided URL in a web browser. Select a Brain MRI image file and upload it. And after a brief processing time, we see 2 images side by side. On the left, we have the original MRI image. On the right, we have the predicted mask showing the segmented tumor. This side-by-side comparison allows users to quickly visualize where the model has identified potential tumors in the brain MRI. We'll provide all code and the diagram file in the video description. If you'd like to support the channel, consider starting a free trial of our new design tool, linked in the description. We'll keep an eye on the comment section for any questions and want to thank you for watching until the end. Please enjoy responsibly.